Thank you. Yeah, so yesterday we had quite an introductory talk to what is a simplicial complex, what is this homology that we're interested about that will allow us to generalize phenomena from random graphs. And today we'll focus on probably the most well-studied model, which is a generalization of the Erdős-Renyi random graph called the random D complex. So I'll give you a quick reminder of what we were discussing yesterday. So we said that the GNP random graph has n vertices, and then edges are added independently with probability p. And similarly, we can generate a d-dimensional random simplicial complex by taking n vertices and adding all the possible edges and all the possible triangles and everything up to dimension d-1. That's what we call the d-1 skeleton. And then at dimension d, we add the d simplexes or the d faces randomly, independently with probability p. So on the left, we have the GNP, the random graph, which can be considered as x1, the one-dimensional random simplicial complex. And here on the right, we have the two-dimensional random complex where we have n vertices, all the edges, and the triangles are random. So we want to focus on this kind of object. And I remind you that I defined to you relatively briefly, but I hope at least the intuition is clear what homology and cohomology are. Basically, it's an algebraic way to measure topological phenomena such as components in a graph, but also holes, which are closed loop without interior, two-dimensional cycles, which are sort of bubbles or air pockets that you have in your space, and higher dimensional generalization of those, which we're going to call K holes or K cycles. And this is done purely algebraically. We have a simplicial complex. We have this, what we define as the boundary matrix, the thing that connects between various dimensions. And then the cycles are the kernel, the boundaries are the image, and homology is the cycles modulo the images, so modulo the boundaries. So it's all the cycles which are not a boundary of something else. This is what we call sort of the structural approach. And cohomology sort of describe the same phenomena, but from a functional perspective. So instead of thinking about lists of simplexes and boundaries, we have functions on the simplexes and derivatives. And so we have what we call the coboundary matrix or operator, and we have the co-cycles, which are functions whose sort of the derivative is zero, and then the co-boundaries, which can be thought of as functions who have a potential, that have an antiderivative. And then HK is the quotient space. And the dimension of these spaces is the same. So at least in the setting that we describe, which is using Z-mod 2 coefficients. Yeah, this is a nice way or a natural way to extend phenomena from components and cycles in graph to something of higher dimensions in a simplicial complex. And what I want to tell you about today is, again, this random simplicial complex model and several phenomena that have been studied by now related to this homology that generalize well-known phenomena in the random graph. So we'll start with what I believe was the first result for random graphs, and then also the first result for random simplicial complexes, just with a gap of some 50-something years. So the very first paper about random graphs by Erdős and Renyi in '59 described the following phase transition for when a random graph becomes connected. There's a little star here because I mentioned it yesterday. The original paper deals with the uniform random graph, which is slightly different, but asymptotically very similar to this GNP. And the phenomenon here is the following: we can choose P, and we want to say what is P, what is the minimum P required so that the graph is connected, and then turn out that there is a phase transition, so the limit of the probability as the number of vertices goes to infinity. If n times P, which is roughly the expected degree in the graph, if it's slightly above log of n, then with high probability the graph is connected, and if it's slightly below log of n, then the graph is disconnected. So that is the main phase transition, and you can also zoom in and look in what happens inside the critical window, namely you take log n plus some constant, so it's not much above or much below, And then you can show that the number of components in the graph has a limiting distribution that is there's only one component plus a random number which has Poisson distribution that depends on C. And from that you can also derive the exact limiting probability. So the probability in the critical window that the graph is connected is this W exponential expression. So this is a well-known result for random graph, and what I want to present next is the result that was established for simplicial complexes, which is very similar to that. But before that, I want to give you an outline, quick review of the proof, because it also, in addition to the result, it's also nice to see the parallels between the ideas behind the proofs, which have a lot of similarities. So let's start with again, just an outline of the proof for this theorem. So the idea is the following. We define by nk here the number of components of size k, components with k vertices. And there are basically two parts for the proof. The first part deals with isolated vertices, namely components with only one vertex. And then one can show that there is this phase transition for the isolated vertices. So if you're, slightly above the threshold, then with high probability, no isolated vertices. If you're below the threshold, you're guaranteed to have some and quite large number of isolated vertices. And if you're at the critical window, you can show that there is a Poisson limit for how many isolated vertices there are. So basically the phase transition we see on the left is coming from what we see on the right for the isolated vertices. And so the second part of the proof aims to show that aside from once you get very close to connectivity, aside from the isolated vertices, there is nothing else. There's just one giant component, as stated here, there's a giant component and isolated vertices and nothing else in between. And to do that, we basically count all the possible components that we have, which are not isolated vertices and not the big component that we have anyway. And then we can show that with high probability, the number of those components is 0. So we can show that there's nothing else but the isolated vertices. So this is the idea. Just let's quickly see how each of the parts is done. Start with analyzing the isolated vertices. So it's a relatively standard combinatorial probabilistic approach. You just define an indicator function for each vertex, testing whether it's isolated or not. And then the number of isolated vertices would be the sum. So to compute the expectation, you have n vertices, and the probability for each vertex to be isolated is this thing, 1 minus p to the power of 1 minus 1. The reason is, right, you have n minus 1 candidates, n minus 1 potential neighbors, and you want each of them not to connect with your vertex, and the probability for each edge not to be present is 1 minus p, so you have to multiply those probabilities. In the regime we're studying, this can be approximated by this n times e to the minus p. You can also similarly calculate the second moment. So you have a double sum, and then you split it between the cases where I equals to j, that would be the first part, and then I is different than j, simple combinatorial calculations, and then you can show basically that the variance has the same limit. So the expectation behaves like this term, and the variance also behaves like this term. So you have roughly an estimate to how the isolated vertices behave. Now, if you're here above the threshold, you plug in log n plus w, then you'll get that the expectation vanishes, and then just Markov inequality will tell you that with high probability you have no isolated vertices. If you're above the threshold, then you can show that the expectation blows up and the variance blows up, and then you can just use the second moment of Chebyshev inequality to show that you're guaranteed to have some isolated vertices, and in fact quite a lot. And if you're in between, then you can estimate the other moments, the use method of moments to show that there is a convergence to a Poisson distribution. So this is a relatively simple calculation. This is one of the things that is nice about this model, that the calculations, the combinatorics is nice to work with. So we show that there is the desired phase transition for the isolated vertices. And as I told you before, the second part would be to show that there's nothing else, only isolated vertices. So in order to do that, we use an upper bound that uses the following fact: every component that we have must include inside it a spanning tree. Right? The spanning tree is a tree that consists of all the vertices in my component. Right. So for example, if this is a component in my graph, then there's more than one spanning tree, but there's at least one, maybe this thing. Okay, so this is a spanning tree of my component. And you can use what is called Cayley's formula, which tells you what is the number of possible trees on k vertices. And this is k to the power of k minus 2. So this is a result in combinatorics. And now if you want to evaluate the expected Emmanuel n star is the number of all components with vertices between 2 and n over 2. So it's everything which is not an isolated vertex and not the giant component. And then you can just sum up and with a rough bound. So you have n choose k possibility to have subsets of k vertices. In each possible component, there are these many options to have a tree. You have p to the k minus 1. That's the probability for all the edges in the given tree that you're looking at to be present in the graph currently. And then you want also for this subset of k vertices not to connect with anything else. So right, you have k vertices over here. You want them, and you have n minus k other vertices, and you want all of these vertices not to be present, right? From this vertex, but also from this vertex, you want everything, all of these things to be disconnected. So in order to make sure that this happens, you have this probability over here. It's 1 minus p to the power of all the edges going from these components to the remainder of the vertices in the graph. And so this is a very rough bound, but one can show that it's small enough. So it goes to 0. And then again, you calculate the expectation, and Markov inequality tells you that with high probability, n star is 0, namely there's nothing but the giant component that has almost all the vertices and the isolated vertices, and nothing in between. So this is very briefly the proof for this fundamental result by Odesh and Rennie for the GNP graph. And as I said earlier, what we want to do now is to state the result in higher dimensions for the random D complex, and also tell you some parts of the proofs and how they relate to what I just described. Again, as yesterday, please stop me or ask any questions if you have. Okay, so this is the theorem I showed you before for the random graph, and what I want to highlight is the following. When you look at the GNP, I told you before, you can think of it as just x1 and p, it's the one-dimensional random simplicial complex. And the question about whether G or not is connected in the terms of the homology I was telling you about yesterday, it's the same as asking whether the zeroth homology is trivial. Right? When the complex is connected, or when the graph is connected, that's the trivial zeroth homology, meaning that you don't have any other components. And one last bit is when you ask about the number of components, this is what I called yesterday beta 0, the zeroth Betty number, the dimension of H0. So in fact, this whole statement can be phrased in terms of homology. And what Lineal and Shulam did was sort of to take this, now replace right, the 1 here and the 0 here with an arbitrary dimension. And what they got is the following really nice theorem, which, as you can see, when one stands by the other, they're very similar. So here what we have is we have a random D-dimensional complex, and then we have a phase transition that just as before. So here we have a one-dimensional complex, and the phase transition was for age 0. So similarly, here we have a D-dimensional complex, and we have a phase transition for the homology in dimension D-1. And the phase transition is very similar. The only difference is that now we have D log n instead of log of n. And similarly, also the second part, the Poisson limit can be proved. Again, we have the D log n. and the d factorial here. But these are the main differences. And one of the really nice thing about this theorem is if you take d equals 1, you get exactly the result on the left for the random graph. So it's a really nice and natural generalization from the graph case to the simplicial complex case using this language of homology. So Lin and Meshulam proved it first for two-dimensional complex. That's in 2006, and they coined the term homological connectivity, sort of a generalization of the connectivity phenomenon. Meshulam and Wallach later generalized it for any dimension, not just two-dimensional complexes. And the second part, the Poisson part, that took some 10 years to prove, and that was in a later paper by Cayley and Pitel. Okay, so we have this generalized theorem, and now I want to tell you again the outline of the proof and how it's similar to the proof that we saw before for the random graph. Okay, so I remind you when we talked about the GNP a few minutes ago, then the proof, what it showed is that the very last component that we have before the graph is connected are isolated vertices. We have nothing else. And similarly, what the proof here includes is the observation that before, right, what are we looking at here? We have, maybe I should scroll back to the picture. Right, so we have, this is in dimension 2, we start when we have no triangles, we have many holes. And as we increase the probability, we have more and more triangles filling in those holes until there are no more holes or no more one cycles, right? So so similarly here, right before all the cycles get filled in, which is what we call homological connectivity, the only cycles that we have are coming from what we're going to call isolated d-1 simplexes or d-1 faces. What do I mean by that? So an isolated vertex is a vertex which is not lying on any edge. And similarly here, an isolated simplex in dimension d-1 is such that it's not on the boundary of any d-dimensional simplex. So for example, if this is your simplicial complex, all the edges here lie on some triangle, except for sigma here on the right, which is not part of any two-dimensional simplex, and therefore sigma here will be considered as isolated, an isolated face. And the observation here is that before we reach this homological connectivity, this is the only thing that we have. We have cycles that are generated by this thing. Now, before we continue to the proof, just it's very clear in the graph case why isolated vertices are contributing to the, or are preventing connectivity, because each vertex is a component of itself and it's not connected. Why is it the case here that d-1 isolated faces are contributing extra cycles that we don't want to see? So you can view it again from both angles, from the homology angle and from the cohomology. So from the cohomology angle, right, you can look at this cycle I marked in yellow on the left. So maybe I'll denote it by gamma. So this is a one-dimensional cycle in the picture, right? Or in general, this will be d-1. And it's not a boundary of anything for the simple reason that this face is not on the boundary of something, right? In order for a cycle to be a boundary, it means that all the edges are coming from the boundary of some two-dimensional shape, but this cannot happen here. So this triangle on the left will definitely contribute something, a class, to the d-1 homology, okay? Or as you see in the picture, it definitely contributes a hole that we have. So this is from the homology perspective. From the cohomology perspective, what we can do is we can look at the, the indicator function for sigma. So in cohomology, we look at functions. So we look at a function that places 1 here and 0 everywhere else. Okay? Now, first of all, this function is a cocycle because if I remind you what is a cocycle, we take the co-boundary, namely for each simplex, we sum the values on the boundary, and then it has to be 0. So take any simplex that you have here, any of the 5 simplexes, the sum of the edges is always 0. The one here doesn't interfere with that because it's not part of any simplex. So we don't care about the sum of these 3 edges because there is no simplex there. Okay, so this is considered a D-1 cycle because the co-boundary is 0. It's also not very complicated to show that it's not a co-boundary. And therefore, it's an element in the D-1 cohomology. So it's a, so to speak, the derivative of this thing is 0 along all the simplexes, but there is no potential. It's not the derivative of anything in a lower dimension. So there are 2 ways to approach that. And in fact, the proof here will take the cohomology approach. We'll use the functional approach in order to prove the homological connectivity phenomenon. And that's what I want to show you next. Again, you'll see how it's in a way very similar to what was done in the graph case. So here is the main points of the proof. So we're taking the cohomology route. We're going to think about functions from the D-1 simplexes to Z2 in our case. And recall that in homology, we care only about those equivalence classes. So we don't care about individual functions, but only on classes where the sum of 2 functions is a co-boundary of something. Now, for each class, we will choose one representative. We call it F star, which is a representative with a minimum support. The support is the number of, the faces on which this function gets the value of 1. So out of all the functions in this class, we're going to take the one with the smallest support, and we call it F star. And what we want to do, we want to go over all the possible functions that exist on our complex. And we want to see if one of them happens to be a cycle, a D-1 co-cycle, sorry. Okay. And the point is that since we only care about equivalence classes, we can go over, we don't have to go over all the functions, we can only go over those with the minimal support. And that's what linear and Meshulam in fact did. So instead of checking all possible functions, they're going to check all the possible functions with the minimum support, one from each class. And I will have a similar notation to what we had before. So nk now will count how many such functions there are with minimal support, where the support has exactly k, so they get the value of 1 on exactly k faces, and such that this function is indeed a co-cycle in my random complex. Okay? And notice that when I take k equals to 1, so I'm looking for functions whose support has size 1, so they get the value of 1 only on one face, and this is exactly the number of isolated faces. Because I showed you before, the indicator function on an isolated face gives you a co-cycle. And similarly, the proof will split into 2 parts. One part will be analyzing the n1, the number of isolated faces, and the other part will be to show that we don't have anything else that is not an isolated faces. Okay, we don't have any of the other possible function that could be a co-cycle. Okay, so part 1 is again, it's a simple part of the proof, very much like in the connectivity of the random graph. So we'll just show briefly the expectation calculation here. So let's say I want to count how many isolated faces I have. So I'm looking at simplexes in dimension D-1. So overall, I have n choose d, many of them. And now for each simplex, right? So each simplex has d vertices, and then it leaves n minus d vertices outside. And what I want to make sure is since I want this thing to be isolated, it means I don't want it to be part of any triangle in this picture or d simplex in the general case. Then I want to make sure that that this simplex doesn't appear in my complex, right? My complex has random d dimensional simplexes, so every triangle in this picture can appear or not with probability p. And if I want this edge to be isolated, I need all of these triangles not to be present in my complex. So the probability for that is 1 minus p to the power of how many triangles I have, which is the number of vertices I have on the right. And this can be also approximated with the exponential term. And then again, if you're above the threshold, this term will go to 0. And the factor of d in the threshold comes from the fact that we're going, instead of vertices, we're going over d minus 1 simplexes, and we have n choose d, many of them. So that's the power of d. So it's very similar. Above the threshold, the expectation is 0. Below the threshold, use a second moment argument to show that it's definitely positive. And if you're inside the threshold, then you need to evaluate moments and show that the number of isolated edges or faces converges to a Poisson distribution. Okay? But this part is relatively straightforward. It's just moment calculation, which can take some space, but the second part is much more, is the heart of the proof. Okay, so we have very much like the graph, for the isolated faces, we have the phase transitions that we want. And now the second part would be to prove that there's nothing else except for isolated faces. Okay, so this is the second part, and I'm going to use similar notation to before. So n start will count all the possible functions, right? It's cohomology, so all the possible functions whose support is bigger than 2, that can be co-cycles, that can make the homology not be trivial or prevent homological connectivity from happening. So here f will be such a possible function, and we assume already that it has a minimum support. We said it's enough to consider those. And the main idea of the proof is to look at the following thing. For every f, we define b of f to be all the simplexes in dimension d, such that delta is the co-boundary. So if I take the co-boundary of f on sigma, it's going to be 1. Okay. Let's see an example, and I think that will be help understanding. So suppose that this is just an example for a possible f. So I'm looking at function on the edges, which is 1, 1, 1 here, 1 here, 0, 0, 0, 1. Okay. And I have 6 simplexes in my example. Now I'm looking for all the simplexes among sigma 1 to sigma 6, such that the co-boundary value is non-zero, or it's 1. Okay. So what I'm going to do, the co-boundary again is just the sum of the values of the faces. Okay. So the sum here is 1 plus 1 plus 1. It's 1 because we're using Z mod 2 coefficient. So right, this simplex is going to be in BF because the sum is 1. On the other hand, the simplex over here, we have twice 1, so that the sum is going to be 0. The sum here is 0. The sum here is 1 again. So I'm going to mark it. And I think the rest are also 0. So 0 here and also 0 here. Okay. So in this example, BF is going to be sigma 1 and sigma 4. Okay, so I'm taking a given function f, and I'm looking for all the simplexes where the derivative or the co-boundary is non-zero. Okay. By the way, this is right. In order for the co-boundary not to be 0, it means that we have an odd number of faces on the boundary which have the value of 1. Right. So this thing is the same as saying that we have an odd number of 1s on the boundary. Right. So here it's an odd number, here it's an even number, so it's not included. And now, why do we care about this B of f? The point is that we want to check whether f is a co-boundary, sorry, a co-cycle or not. And I remind you, a co-cycle means that the co-boundary is 0. And if I'm taking this particular f in this example here, and if sigma 1, for example, will be in my complex, right? The sigma are the random parts in my complex. That's the one I generate with probability p. So if sigma 1 is going to appear in my complex, it's going to automatically exclude f from being a co-cycle because I have a simplex where the co-boundary is not 0. Okay, I can allow sigma 2 to be in my complex. I can allow sigma 3 to be in my complex, but I cannot allow sigma 1 and sigma 4 to be in my complex because if I do, then immediately f is not going to be a co-cycle. Okay, So that's what I wrote here. The set that we have in B of F, the set of all simplexes where the co-boundary is 1, is what will prevent F from being a co-cycle in my random complex. Okay, and this is the main point. Please ask me if it's not clear enough. Okay, and now the key point is a proof is the following thing. If we want F to be a co-cycle, this will happen if and only if this set B of F doesn't exit the random complex, so the intersection is empty. So there's none of the simplexes that are included here enters the random complex. Okay, so if none of the simplexes appear in the complex, then the co-boundary will be 0, and then F will be a co-cycle. But if at least one of them will show up in my complex, immediately this function is going to be ruled out, and I'm going to leave it behind. Okay. And I remind you, what I want to do is I want to go over all the possible functions, and I want to see if any of them can be a co-cycle. Namely, if any of them, once I look at this set B of F, if indeed this entire thing doesn't show up in my complex. And therefore, what we can show is that the expected value of n star can be bounded by, we're going to sum over all the possible functions whose support is bigger than 2. And then we have this set B of F. And we want for each function, if this function is a co-cycle, we know that all the faces in BF must not appear in the complex. And therefore, the probability for that is 1 minus p to the power of the size of B of F. Okay, so this gives us a way, a combinatorial way to now go and look for all the possible co-cycles and see whether any of them can appear. And from here on, there's a lot of hard combinatorial work to do to show that eventually this sum will indeed go to 0, assuring that aside from isolated faces, as we saw before, all the other possible functions cannot appear in the complex. And that's in the critical window when you're close enough to the phase transition. Okay, and this is very similar to what we saw in the random graph, right? There we checked for the isolated vertices and everything, and n star was all the components that are not isolated vertices. And here we're looking for all the functions which are not coming from isolated faces. So not only the result is similar, also the proof or the idea behind the proofs are similar, even though it can get much more complicated. Okay, so this was the first result I wanted to tell you about. And this is the most detailed one that I will be speaking of. The rest, I want to give a quick overview for other results. But this result A is I think it's both the fundamental result for random graph, the very first one, and similarly for simplicial complexes. And I think there's a lot of nice similarities and nice ideas that to generalize a phenomenon from random graph to random simplicial complexes. So I wanted to speak about it in more detail. What I want to do next is to look at other phenomena that are known for random graphs and how they translate to the random complex. So here is another result, again, coming from Erdős and Renyi a year after. So the question there was to look for cycles in the graph and to ask whether or not a graph G has a cycle. And this happens right before connectivity happens when NP was log of n. Now we're looking at NP, which is a constant. So what one can prove is that when NP is constant, there is some kind of a transition for the probability to have a cycle. If it's above 1, if n times p, the expected degree is above 1, then with probability approaching 1, you have a cycle. If it's below 1 and above 0, there is some function here that tells you what the probability is. And if it's much smaller than 1, then you don't have any cycles. So this is, again, the result for random graph. And we can do the same thing we did with the connectivity result and translate it now to call this x1 and p. And saying that a graph has a cycle is the same as saying that before we studied H0 connectivity, now we're studying H1, the number of the cycles in the graph or the holes. Okay? And the theorem that we're going to show next is, again, a nice generalization of that, even though it's not, the phenomenon now is not exactly the same as before. So in the graph case, we took a one-dimensional complex and asked for one-dimensional cycles. Now we're looking at the same d-dimensional complex and asking about the d-dimensional cycles. Okay, the result before homological connectivity dealt with the D-1 cycles. Now we're going to the D cycles. And one can show that there is somewhat similar phase transition. So it also happens when NP is a constant. Now the value is not 1 like here. There is some threshold value that can be evaluated. You have the values here that were estimated in these papers. But the probability will be 1 at some point. Below that, the probability depends on C, and this is how it looks like. And also, if it's much smaller than 1, you can show that there are no D-dimensional cycles. And in this picture over here, you can see the graphs of the probabilities for the various dimensions. So the blue one, this one is for the graph, and it goes continuously until it reaches 1. Whereas for the random D complex, there is discontinuity. So it goes up, and then at some point, it just jumps to 1. So it's a little bit sharper result. This is, there are several papers studying that. The first part here is by Aronstam and Linial from 2012, and the second part was by Nidian and Peled in 2016, and the other one is an early result by Kozlov, 2010. So a few remarks. So notice that we have two processes that we're studying for this D-dimensional complex. Before, when we looked at homological connectivity, we looked at D-1 homology. When P is 0, right, think about a random 2 complex here. When P is 0, you have many, many holes, many cycles in dimension 1. And when you add more and more phases, eventually you're going to fill them all in, and homology is going to die. So you start with the largest possible homology and finish with the smallest one. Okay, and what we showed is that this happens roughly when NP is D log n, sorry. Okay. The D-dimensional homology goes through an opposite process, right? If we're looking for 2 cycles here, air pockets, we have none because we don't have any phases. We add more and more phases, and eventually we're going to start creating those bubbles. And here it's going to be the maximum size of this homology. And what we're looking for here is, right, basically the point. If before for the D-1 homology, we found the point where this thing vanishes, with the holes vanishes, now we're looking for the point where the first cycle appear. And basically what the theorem on the left tells you is that they appear when NP is this value, this constant value. Namely, they appear with probability 1. So these are 2 different phase transition happens at different places. First, we have enough 2-dimensional phases to create, D-dimensional phases to create D-dimensional cycles. And later on, we have enough D-dimensional phases to kill all the D-1 cycles. So this is just a remark. Okay, so I might skip that. Maybe I'll show it without the calculations, but some difference between the graph and the complex is in the graph when you look for cycles, so you can have a cycle on 3 vertices, 4 vertices, 5 vertices, and so on. And if you do the calculations, you get that when NP is constant, you can have each of them can appear. So the expected value, for example, is a constant value for 3, 4, 5, and so on. So when you're in this regime, you can expect to see cycles in all sizes. On the other hand, when you look, for example, at the 2-dimensional complex, and you look for 2-dimensional cycles, so this is a 2-dimensional cycle, the boundary of the tetrahedron. And this is on 4 vertices. And indeed, this has a constant value. You can also have a 2-dimensional cycle on 5 vertices. So this is take all the 2 faces that locks this kind of bubble, but then you can show that the expected value goes to 0. So in the simplicial complex case, basically in this regime, you can only see those smallest 2 cycles or D cycles. which are, in a way, this is an empty, you can think of it as an empty tetrahedron or an empty D plus one dimensional simplex, and everything else will very rarely appear. Okay, so it's very different than what we have here. And this is backed up by sort of the following two theorems, from which the first theorem I showed you was can be concluded. So the first theorem is a statement by Aronstam and et al. From 2013. And what they show is that in this regime, when NP is constant, basically almost what I told you is true. If there is a D cycle in your complex, then there are two options. Either it's an empty D plus one simplex. So if you have a one cycle, it will look like that. If you have a two cycles, it will look like an empty tetrahedron and so on. Or it's very big. It has order of n to the D number of faces in it. Okay, but there's nothing in between. There's not going to be a D cycle on 10 vertices. And the theorem proved later by Linian and Pellet is the following. So you can calculate, or there's a formula how to find those thresholds, and you can show then that the Dth homology below the threshold is either empty, or it consists of, again, those D plus one simplexes. So if you're below the threshold, basically you rule out this option. Below the threshold, you don't have any big faces. So the only thing you're left with are the boundaries of D plus one simplexes. And then you can also derive a Poisson limit for that and so on. And if you're above, then you have those big D-dimensional cycles. And you can also show that the Dth Betty number, the number of those cycles, is very large. So it's roughly n choose D to some expression which is given in the paper, but it's not a nice expression, so I leave it out. Okay, so basically the idea is that the behavior before in the subcritical range is determined by the boundaries of D plus one simplexes, and above that, a lot of big things show up immediately. And that's very different than what happens in the graph, which goes more continuously, because at any range of parameters, we can have all kinds of cycles showing up. And the last thing I want to tell you about is one of the key ingredients in the proofs of both these theorems and other theorems exploring this range when NP is constant and all this kind of phenomena that happened there is looking at the local behavior of the complex in this limit. So a result known before for the random graph GNP is when NP is constant. If you look at the bounded neighborhood of a vertex, you can show that there is a weak limit to the Galton-Watson tree. So it's a tree where the number of descendants always has a Poisson distribution. And apparently a similar phenomenon happened here in the random complex, which I think is interesting. So we need to build the graph from the complex, and it's done in the following way. We take a graph where the vertices consist of all the D minus one and D dimensional simplexes. And we have an edge whenever one simplex is on the boundary of the other. So for example, here, this is my complex. I can start building my graph from E1, and then I will add sigma 1, sigma 2, sigma 3, because E1 is on their boundary. So those will be the descendants. And then for sigma 1, for example, I will add E2 and E3 because they are on the boundary of sigma 1 and so on. So I have this, this boundary representation by a graph, right? So I'm moving all the time from an edge to a triangle, back to an edge and so on. And what was shown as part of the proof for the theorem that I told you about is that in fact, if you take the random D complex, you start from an edge or D minus one face and you build this graph, this graph is going to be a tree, and a tree with a very nice structure. So the most important lemma here is that when NP is equal to C, you can show a weak limit for this graph that I told you about, which is a tree, and it's called a Poisson D tree, where by that, what I mean is that there are two levels at the even levels or the odd levels maybe. Here, the number of descendants is always Poisson with parameter C, and at the odd levels, the number of descendants is always D. So here it's, and this comes from the fact that every D simplex has exactly D plus one faces on its boundary. So it has, if this is a D simplex, it has D elements +1 on its boundary. So it's, but the results state that if we build this graph locally, it looks like this Poisson D tree, and most of the results are derived or use this fact somehow, basically proving stuff first for the Poisson D tree and then translate it back to the random D complex. Okay, so I will wrap up. There are a few other results you can, I'll upload the slides so you can take a look at them, but I'll just conclude now. So I showed you, we talked about the random D complex, and I showed you two phenomena that generalize things known from the random graph case. One is connectivity, which we generalize to what we call the homological connectivity, when the homology in dimension D-1 becomes trivial. And the other is the appearance of cycles, but now not loops, but rather D-dimensional cycles, which can consist of D-dimensional faces. And everything sort of nicely generalized, but this complex is quite well studied on many other topics that are studied. For example, the fundamental group on two-dimensional complexes, proving stuff instead of Z mod 2 to other coefficients. It's a whole work by itself. There are also some interesting results about there is a way to define the spectrum, like the spectrum of a graph. There is a way to define the spectrum of a complex and study it. Very much like spanning trees, there is a notion of spanning A cycles in a random complex, and there are some results on that. Expansions in graphs can be translated to expansion in complexes. And there's also the multi-parameter model, which is a generalized model where you have probabilities for faces in every dimension to appear. So there are a lot of many other results and models to be studied in this context, in this combinatorial context. And I will stop here. Tomorrow, we're going to talk on a different class of complexes, random geometric complexes, which share some similarities with what we talked about today, but their behavior is much different, and we'll see how tomorrow.